We've said how we can get potential from field, but now how are we going to get field from potential? And one thing that really makes this more challenging is we need to think about the direction. Remember that field is a vector, while potential was a scalar. So this gets a little trickier simply because we need to get the direction out of this. So the electric field in one direction, again, S could be X or R, whatever you want, but it's one direction. The electric field component in a direction is given by the negative derivative of the potential with respect to that position. We're going to get a little bit into this idea of partial derivatives, and we're only going to touch on it. If you're familiar with the idea of partial derivatives, hopefully this will make sense. If not, most of our problems are again going to be fairly simple. We just need to think about the fact that potential is defined over 2 or 3 dimensions, however many our problem's in. So we need to be careful about which direction we're taking the derivative in. That's all. So these two directions need to actually agree. Now, if we want our entire electric field rather than one component, we're actually going to need to take multiple derivatives. If we're very clever, we can maybe only do this once if there's a symmetry, such that we can say all of the other directions are 0. So what's going on with this is that if we have our total electric field vector here, when we take the derivative in one direction, we're getting the electric field component in that direction. So in this case, this is basically our S hat. So you can see that this component isn't the entire vector. We would need to also look at what's happening this way to get the second component. So that's where we have to think a little bit about what's going on. Representing this graphically becomes really, really important. So we're going to do a little bit with the math, but then in a second video, I'll be talking about the visual connection between these, the graphical connection. Because if you just pick a direction and you don't actually think about what's happening, this is not going to work very pretty. Obviously, if this is the direction of our electric field, we maybe could have just picked that direction and done this once. So as one example, let's think about a ring of charge. So you've seen the scenario a few times. You have a ring, which is theoretically what that is. There's some center axis, and so we just think about a point on this axis, and we call this the z direction. So you've done this math a couple of times, you break this into pieces, and you can do this either for field or for potential. So let's start with the definition for the potential from this ring of charge at location z, but again, we must be on the axis, and try to get the electric field from this. So you might think that we're going to need to do 3 derivatives and all kinds of crazy stuff, but it's really not that bad. The first thing is that we know that we only have a z component of the electric field. The other components are non-zero. Why is that? Because of symmetry. If you're right on the axis, there's no reason to have kind of a sideways component of E. It's purely, E here is purely going to be E in the z direction. So that's nice. What that means is when we go to do the derivative, we only need to worry about z, we don't need to worry about anything else. So again, remember that there's a minus sign here. There was a minus sign when we integrated, so it does make sense that there's also a minus sign when we take the derivative. So don't forget about that. So I'm pulling out q and 4 pi epsilon naught because those are in fact constants. And so then I'm going to take the derivative of what was on the bottom. Now, if it's been a while since you've had calculus, maybe you're a little rusty on this, one thing that's helpful whenever you have a square root on the bottom is I find to actually write it this way, as it's a quantity to the -1/2 power. Now when I go to take this derivative, I see that I need to do the chain rule. I have a z squared on the inside, and then I have a power on the outside. So that power is going to bring down a -1/2 and make the whole thing go to -3/2, which means it's on the bottom with a 3/2 power. But then the 2z is also going to give me, sorry, z squared is also going to give me 2z. So I see that my 2 and my 1/2 cancels, but I'm going to get a minus sign that comes back and cancels this, and I'm going to have a z on top. So my answer then, like I said, that minus sign goes away, I have a z on top, and now the bottom term has become to the 3/2 power. So this is the electric field component in the z direction, but from symmetry, we say that's the only one we're worried about. So this literally gets to be my entire field vector as long as I multiply that by z hat. You can double check. This was the electric field from a ring of charge, and this is the electric potential from the ring of charge. And if you wanted to, you could in fact go backwards, start with this electric field, and then integrate to actually get up to your potential. So you can go back and forth between these two quantities. Last, think about this derivative relationship when doing plotting. So if you have a plot of potential that, like this case, is piecewise with these straight line segments, use the derivative to get what the electric field is in each case. And in this case, this would be dx. But remember that there's a minus sign to get E. And in this case, it's just the x component of E. So if this is what our potential looks like, our electric field is negative here. It's then positive up here. And note that it's 0 in between. So whenever you have 0 electric field, your potential is not changing. I've mentioned this before when we talked about the potential and field inside a sphere. Be careful, because if you have a region of 0 electric field, that doesn't necessarily mean your potential is 0. It just means your potential is not changing. So that's a little bit tricky to think through.